All right, why don't we get started? We're a little past 6:30. And I'm sure there'll be others joining as we go. Welcome to our last event for this section year. We're getting some uh, Oerlikon Balzers presentation from Bao on the coatings for mechanical components. So it's going to be about a 45 to 50-minute presentation. And then we'll follow that up with Q&A. Just going to talk briefly about SAE Chicago. If you want to go to the next, there we go. Most of you are probably SAE members, but if not, if you're in the area, it'd be great to have you join us as a member. We're one of the largest, most active sections in SAE International. And you can see the benefits there between networking, events like this, company tours occasionally, and then professional development. For students, I'm not sure if any are joining us tonight, but we've had a few university students part of our events and also our monthly board meetings. We have approximately, excuse me, 800 and so total members, about 750 professional, and then a fluctuating number, about 130 university students from UIC, Northwestern, NIU, Illinois Tech, and Bradley. Just a quick overview of our current board. This ends next month on June 10th. What was it, 9th? I don't have a calendar in front of me. Whatever the next second Tuesday in June is our last meeting of the year. And at that meeting, we do, it's June 11th, 6 o'clock. It's going to be at Navistar. And we'll not only do a year in review, set up our plans for next year, and then at the end, we'll vote for the section officers and the positions that are shown here. This is our current board. You can see the wide variety of companies and positions that are representative of the people on the board. Everywhere from early in their career. We had some students, like I mentioned earlier, that are part of this, and then others in their senior end of their career, and also some retirees. So it's a good broad spectrum of companies and engineers. To follow us or to get more involved, you can check out our website at chicagosae.org. LinkedIn, we post events like this also for getting the word out, and we're over, I think, 500 followers on that, so it's a good broad audience, and to a lesser degree with Facebook and Twitter, or X, I should say. The only upcoming meeting we have is our year-end meeting in June, like I said, June 11th. Let me know if you're interested in participating in that. I can get you the information. There's a chance that we're going to have an event around the NASCAR weekend in Chicago, the race in the streets. Working with the local marketing folks for NASCAR. Intended to initially be a student event, but we're getting pretty late in the year, student year at least, to have them stick around or come back to the area if they're from out of town to participate in that. So more to come on that. So you can watch either our website or LinkedIn. And right now we don't have anything scheduled for fall, but there are probably 3 or 4 very positive meetings that are, or events that we may have even in person for the fall. So again, take a look at our website and follow us on LinkedIn. So with that, Troy, I will turn it over to you.
Yeah, thank you, Tim. Hello, everybody. My name is Troy List. I am the treasurer for SAE Chicago. And before we get started with the presentation, a little bit about our speaker, Bao Feng. Bao holds an MS, or Master's of Science in Mechanical Engineering from Louisiana State University, and a Master's of Business Administration from the University of Illinois. He started at Oerlikon Balzers as a product manager for Precision Components in 2020. In that role, he's been leading marketing and commercialization of surface engineering solutions. Prior to going to Oerlikon, Bao was an engineering specialist in the surface engineering and tribology group at Caterpillar Inc., where he held various positions in the R&D and manufacturing space for heavy machine systems. He was there for 20 years and accumulated technical expertise in PVD coatings, which I think he'll speak a lot about tonight, and tribology. The technology he and his teams developed and implemented have created extensive business value, and he is the inventor of 7 patents. And before I turn the floor over to Bao, just a comment about the question and answer session. The way we'll work this is if you can enter your questions into the chat, we'll take those in the order in which they come. Depending on the number of questions that we have, I may either read them and for Bao's benefit, or if there are just a few of those, we'll have you unmute yourself and present your own questions. So with that, it's my honor to turn the floor over to Bao Feng, and looking forward to a great presentation. Thank you.
Hey, Troy, are you sharing your screen? Can I share my screen so I can operate from my end?
Yeah, I'm sharing right now, Bao. You should be able to.
Okay, let's see. I'll share my screen. I don't know why. Can you stop sharing first? I don't know how to turn on my sharing at this stage. Okay, thank you.
Yep.
Let's see. Oh, what's going on here? I cannot share. Okay, getting close to it. Okay, this window here, share. Okay. Can you let me know? Does the sharing function works okay?
Yep, you're coming through.
We
Okay,
can see
great.
it.
Okay, thank you. Thanks, Troy, for the introduction, and thanks for the kind invite from Chicago SAE. Good evening, everyone. It's my pleasure to be here and to share some professional experience on PVD coatings. I guess, like Troy already covered, the interactive section will be left to the very end of the presentation. So if you have any questions, feel free to write them down. I'll be glad to answer them after the main body of the presentation. So with that, can anyone confirm, is my voice come out okay?
Just fine.
Okay, great, thank you. Let me see if I can switch. Okay, so I'll start the presentation with geography questions. What is the country between Austria and Switzerland? I guess most of you can probably answer it correctly, but I doubt it if you can spell or pronounce it correctly. It's called let me try it. Liechtenstein. Let me know if I did it right. Give me a thumb up, right? So this is the Balzer. Balzer is the southernmost village in Liechtenstein. And overall, this country has about 38,000 residents, about 5,000 people living in Balzers, Liechtenstein. And you can see the global headquarters buildings and our R&D center in Balzers, Liechtenstein, next to the hill of the Gutenberg Castle. So next time if you travel to Liechtenstein, you can tell other people, yeah, I know a company is making PVD coatings called Oerlikon Balzers in this place. So today we're going to talk about a little history about our company and what we do. And we're going to spend most of the time on PVD coatings and properties and functions. And we're going to also touch base on the coating processes, how the coating was deposited. And since this is an SAE event, we'll give some examples for PVD coatings on automotive applications. Balzers is the first company commercialized the PVD technologies on industrial applications. You can see that small biojar-shaped coating reactors in the 1940s and some manual operations around it. The company was founded by these three brilliant individuals: a university professor from Liechtenstein and the CEO of Oerlikon, the mother company at that time, and the Prince of Liechtenstein. If you're interested, feel free to check out their bios from the internet. I believe there are some interesting stories behind each one of these individuals. And of course, over time, our company has grown to much bigger size. Now we have over 5,000 employees around the world in 37 countries, and we have over 1,300 coating machines installed around the world. We're truly a global company at this point. So the market segments we cover are pretty much everything. Cutting tools, molding tools, automotive components, aerospace components, medical, semiconductors, even luxury goods with decorative coatings. If you look around yourself, most likely there's some items are either coated by us or our coating has been involved in the manufacturing processes for those products. What kind of products and services we provide to our customers? So under the Oerlikon umbrella, these are the coating technologies we offer. We provide coating material, coating services, and coating equipment. For Oerlikon Balzers, we especially focus on this red arrow pointing to the PVD coatings. We also do a little bit of the conversion coatings, like the plasma nitriding, carburizing. Those techniques we typically use for providing a strong support for the PVD coating on top for some special applications. When we talk about PVD coatings, its materials family has a set of special properties. One of the special properties is the thin geometry. Take a human hair as an example, is 100 micron thick, but typical PVD coatings we're talking about from sub-micron to few microns, a very small fraction of a human hair. And for that reason, a lot of our customers also take advantage of PVD coatings. They use it as a banded solution, meaning they don't need to change the component geometry to accommodate the coating thickness. They can simply just apply this coating on an existing design to see it will work better or solve the issue. And also that's the reason why people interchangeably using thin film coatings for PVD coatings as well. The type of applications normally we're dealing with are a lot of times tribological in nature, meaning is about friction and wear. And for this type of applications, we're dealing mostly two material categories. One is crystalline ceramics, mostly cubic structure, transition metal nitrides, carbides, or oxides. Their property is pretty straightforward, very hard and non-metallic. So they can provide erosion resistance, abrasive wear resistance, adhesive wear resistance to the components, and sometimes the oxidation resistance because the ceramics in general are inert to environment. So I will spend more time to talk about the other material category, which is carbon-based coatings. They're mainly made of amorphous carbon. But at the same time, they contain some sp3 electron bonded structure, like we can find in diamond, and some sp2 electron bonded carbon, which often we can find in graphite. I believe about these content normally in short range order, meaning they're very small. At the same time, there's very small quantity of them in this type of material. I believe someone in the marketing group came up with the name called it diamond-like carbon, and right away hits the market, and people like that name. It's obvious it's because people value diamond much better than graphite. Otherwise, we can well call it as graphite-like carbon. For materials engineers, this is probably exciting, but if you're not a materials engineer, I'm sorry to bore you to death. This is titanium doped amorphous hydrocarbon, or titanium DLC. This is a cross-sectional high-resolution transmission electron microscope micrographs. You can see the atomic level resolution here, and those clear lattice fringes representing the titanium carbide crystals. In average, it's a size about 2 to 5 microns, embedded in amorphous carbon matrix. So this is a proof of this nanomaterial. So look at those clear lattice fringes, really impressive. And why nanomaterial matters, right? Because typically the nanostructured material will bring in a different set of properties. For example, higher strength or higher crack resistance or different surface energies. These properties can be used for material improvement or different functions. The microstructure of the coating dictates the mechanical properties. On this chart, we put I also put the hardened steel, about HRC 60 converted to gigapascal hardness, 6 or 7 gigapascal hardness, and bulk silicon oxide, which often can be found in sand, and bulk tungsten carbide, which often used as cutting tools to cut hardened steels. And we can see that for the diamond-like carbon coatings, it has a very broad range in terms of mechanical properties. From the very top, close to the diamond hardness, 100 GPa, to the other end of the spectrum, about 10 or so GPa, tungsten doped DLC. So the point over here is, with this big range of mechanical properties, we can use different coating technologies or manipulate the coating parameters to fine-tune the properties of these coatings for different applications. For example, for cutting tools, we can use this extremely hard diamond-like carbons, but for sliding components, we can use these softer diamond-like carbons while for wear resistance, while providing good lubricity. So we talk about the thin geometry and this extreme hardness of DLC. Another special property of this coating is low friction, right? This is an early study by Ken Holmberg. He's the author of the coating tribology textbook. He was trying to compare the DLC coated steel against not coated steel in a sliding or tribometer test, reciprocating linear tribometer test. Also under different lubrication conditions, with dry versus, I believe oil 1 is a mineral oil, and oil 2 is hydraulic oil with EP additives. The key point over here is with the DLC coating, you can bring the friction coefficient of the steel down from 6.6 level to about 0.1 level. Is a similar reduction as when you apply traditional oils or the oils with EP additives. So what that means is for some dry contact condition, you can use DLC to replace the traditional ways of lubrication. So why is that? Why there's a low friction for DLC, right? People at Naval Research Lab NRL performed this creative experiment in the early 90s. What they did was using a DLC coated steel ball sliding against the glass, excuse me, a glass slide. And they look because the glass slide is transparent, so they were able to use a Raman spectroscopy to look at the contact interface from the other side of the glass slide. So what they were able to see was that is during the breaking stage, a transformation from in the transfer film, transformation from amorphous carbon structure to a graphite structure. Of course, we all know graphite is a good solid lubricant because of due to its layered structure and easy to share. And we know many of those solid lubricants like tungsten disulfide, moly disulfide, or PTFE. But the difference of DLC is the DLC will last. It has a high wear resistance. It will provide the low friction at the same time. It will last for a long time, in opposed to the other solid lubricant I've talked about. Those coatings only provide the benefit at the very beginning of the contact, then get it wiped off in short time. And this study has been repeated by hundreds of researchers from different research groups. And the code is a graphitization phenomenon and is real. It has been confirmed over and over. And how that friction, low friction behavior compared to traditional surface engineering technologies, for example, hard chrome or nitriding. As you can see, for hard chrome and nitriding, they started as a high friction coefficient under dry contact, and very soon they have a scuffing failure. But for DLC, it goes through the initial breaking stage as a little higher friction coefficient, but then the friction coefficient starts to come down to a steady state, and then continue at that condition for a long time. So we talk about low friction of this coating system, and I also want to talk about the wear, because wear and friction come up, in our impression, they come hand in hand most of the times. The reason I bring these like aged charts from a study from 1950s is because the person conducted this research, Ted O'Burrow. He was a staff metallurgist in Caterpillar Tractor Company in the 1950s. And he is also a member of SAE Chicago. So I didn't make this up. Feel free to verify that. Before this study he performed, people that believed in the classic R-chart wear equations were assessed the hardness is responsible for the wear resistance of the material. But what Ted, through his experiment, he found out there's another parameter that is more relevant to the wear resistance of a metal. He called it a model, mainly is Bernal hardness over Young's modulus. If you put that in the stress and strain curve, you can easily figure out what that means. That means the elastic strain limit of the material, meaning how much elastic strain the material can take before it breaks. So by that definition, it already sounds making a lot more sense, right? So that was a groundbreaking research developed by SAE member, and even today there's still follow-up research based on this research result. So how the PVD coatings stand on that model scale? I put in this the test results from nano indentation on the PVD coatings for including the diamond-like few different diamond-like carbons and titanium PVD titanium nitride, chrome nitride, side by side with hardened steel and bulk tungsten carbide and even diamond. And most of those materials are much hotter than the hardened steel. And for that reason, they were used for cutting tools to cut hardened steel. But at the same time, in terms of H/E or the model, you can see the diamond-like carbon coatings in overall has an average about 3 times of H/E of hardened steel. So that's how the coatings provide the wear protection for the base material, because the coating is the outward facing surface making contact with the counter surface. So I mentioned the DLC has low friction and high wear resistance, but I'm not suggesting the DLC will not wear, right? As a matter of fact, the old material wears, even a diamond wears, right? But most of the material wear in engineering applications, they'll create debris particles. And those debris particles, if not get brought out from flushed away from the contact interface by lubricants, then they will become wear particles and to accelerate wear. But the DLC type of coating is different. So we started from engineered surface under, of course, under microscope, no surface is perfect. So you still have these peaks and valleys, and the coating is because it's so thin, it will follow these surface contours. And while the coating is breaking in the counter surface and also breaking itself, it will create the debris particles, which mainly we talk about the graphitization effect, will fill up the valleys of the counter surface and form a transfer film with low friction properties. So this is a different mechanism provided by the DLC type of coatings compared with the traditional contact surfaces. There's another piece of evidence to confirm that behavior. If you put this contact surface, the coated surface under atomic force microscope, so you can see at a nanometer scale what the surface look like. It started as these surface with bumpiness texture, like a sandpaper. After breaking and breaking itself and breaking the counter surface, that surface will become like ideally mirror-like surface, even under a nanometer scale. If we look at it, there's a 2 nanometers surface roughness. And at that time, the coated surface will lose its capabilities because it's so slippery. It's already lost its capability of breaking the counter surface. So at this point, you would hope you already finished the breaking process. Otherwise, you'll get in trouble, right? There's a piece of research published by Steve Harris from Ford Motors research. Numerically developed some numerical analysis and the more detailed description about this phenomenon. It's a really interesting reading material. And since Steve used worked for Ford Motors, he's probably a member of SAE also, but I didn't know that. So feel free to confirm, Troy or Tim. So I mentioned the friction, the low friction, and wear resistant, and the mechanical properties of DLC coatings, but by no means I'm trying to indicate the friction and wear are material properties. As a matter of fact, friction and wear are system behaviors. This is a good example. This is a lubricated wear test. We have different DLC coatings side by side compared with PVD deposited chrome nitride coating. And surprisingly, because we mentioned the low friction and wear resistant with DLCs, but surprisingly, the chrome nitride coating in this case at low contact pressure level, it has almost no wear. So we did a further study and found out there is micro cracks on this particular chrome nitride, which facilitate a lubrication reservoir at contact. We put that on a classic strike back curve. The Y is the friction coefficient, and the X is the lambda ratio, describes the lubrication conditions. On the left side, you have asperity contact, high pressure, low speed. You squeeze the lubrication films completely out. You will rely on the DLC type of coating to provide the lubricity. And you move to the right, come to the mixed lubrication regime, where you do have a little bit lubrication, but at the same time you still have the asperity contact. That's where that special chrome nitride coating will work best. And keep moving to the right, you get into the electro hydrodynamic lubrication regime, where you have full oil film separation between the contacts, between the surfaces. At that point, you no longer harvest the benefit of the coatings. This is a typical contact condition for automotive applications, where you have low contact pressure but high speed. But also keep in mind that you also have frequent start and stop conditions, where you throw the contact lubrication conditions back and forth between boundary lubrication and hydrodynamic lubrication. In other words, you still need the coating protection for the components. Sometimes the corrosion resistance of the material of the coating is very important. The PVD coatings, and because it's really thin and it has some natural porous structures, so it will allow some corrosive substance to go through the coating and start corrosion at the substrate and coating interface. At that point, your coatings will start to come off. So there are a couple of ways we can improve that corrosion resistance of coating. For example, we can increase the coating thickness. And as you can see in this standard soft spray test, that improves the corrosion resistance. And another thing we can try to apply laminated layers, the multi-layers coatings. So it will interrupt those through pores or through holes in the coating. And you can see the corrosion resistance will become much better and comparable to hard chrome, much thicker hard chrome coating. Some of the tribological contacts are designed in electrical field, or some of the surfaces are actually used for electrical applications, right? So that requires, we have coatings with different electrical conductivities. We have titanium nitride, very conductive, close to the conductivity of irons. And we also have some options like the silicon doped ADLC that has the dielectric properties similar to typical ceramics like the zirconium nitride. So the point is we have a lot of options for different applications in terms of electrical resistivity. And this chart shows the oxidation resistivity or the temperature tolerance of the PVD coatings. Mainly about for the ceramic coatings covers the high temperature applications, for example, tools or molds or rocket applications, rocket engines. For some reason, the DLC coatings is not included in this chart, but I can tell you, if you trust my words, the DLC will be on the left side of this chart. Under 350 degrees Celsius, it will work well, but beyond that temperature, the DLC coating will start to degrade and lose its function. But in the practical tribological applications, most of them are under that 300 degrees Celsius, so the DLC coatings will work fine. So I brought up the idea of wear and friction, not a materials properties, their system behavior. So when we look at the tribological systems, we not only look at the materials, but also look at the lubrication, the degrees, contact pressure, the speed, everything counts, right? So that's how we analyze a tribological system. And also in terms of wear, especially for a primary wear mode, there are so many different kinds, like abrasive wear caused by hard particles, adhesive wear from metal to metal contact, and the fretting and the pitting. You can see all these type of wears in the field, but the good news is many PVD coatings can provide protections against these wear modes. And they extended the life, reduce the friction, and they extended the life of the components. So to this date, I can say most of the tribological issues connected with coatings and surface engineering has been studied. So it's pretty much exhausted in the research field or even in practical applications. And there's no need to reinvent the wheels. We can analyze the contact condition and easily come up with a optimized surface solutions for it. And another point is we always promote this idea to the design engineers of components or machine systems that coatings is a design element, right? That means we need to consider the coatings at the design stage. So that way we can maximize the benefit of coating. For example, if we consider the coating can reduce the friction, we can reduce the size of the components and improve the power density. That's just one of the examples. In opposed to like the banded type of usage of coatings, like we previously mentioned, that's not very often is not going to maximize the benefit of coatings. So we'll switch gears and talk about the coating deposition processes. The coating is delivered in a high vacuum coating chamber, like one of these. From the outside, it would look like a heat treat furnace, but inside you got sensors, coating sources, and the vacuum pumps. So inside of the coating chambers is a phenomenon called a gas discharge or glow discharge. If we all learned physics, we know Langmuir, he is the first person that named this phenomenon as plasma. Of course, this is different from this term is used in the medical field. The plasma over here is referring to the quasi-neutral gas phase with similar number of electrons and ions. While the electricity across a thin air breaks the gas molecules into ions and electrons, it will emit light. It's like a similar effect in the polar lights. right? And there's critical parameters like in the Paulson's law, which defines the lowest voltage to generate glow discharge or plasma at a certain vacuum level, or the Debye lens defines the mean free path of gas particles in free space, eventually translated to the coating properties. So you can imagine in the coating chamber, there's these green colored coating source, and also the sample table in the middle where it carries the substrate and create 1x, 2x, or 3x rotations. So the purpose is to have the to be coated surface evenly exposed to the coating source. So this is a line of sight process. Meaning wherever in the coating chamber can be seen by the coating source will get coated with good quality coating. Otherwise, that surface will not get coated or get coated with coating with poor quality or very thin thickness. So you can consider that's the limitation of the coating process. So I guess no technology will work for everything. So this is an example of that. So in terms of compatible substrate material, actually it's pretty wide span, if you will. The PVD coatings can get on to different hard metals or soft metals, ceramics or non-metallic ceramics like polymers or plastics. All kinds of substrate. But one thing you don't want to coat with PVD coatings is the porous materials, because the pores on the material absorb the moisture or oil and other contaminants. During the high vacuum process, they will outgas and cause contamination and poor coating quality. So porous material is something we certainly want to avoid for PVD coating process. So next, I want to talk about a few examples about automotive for automotive applications. I like this slide because it gives a representative applications for almost every scenarios, every industries, right? For example, in automotive industry, we started with the engine piston liner, piston rings, and wrist pins. In this condition, we're trying to avoid scuffing failure and reduce friction to improve efficiency. So DLC and chrome nitride is probably that special chrome nitride very often used in these scenarios. And also diesel injection applications for injectors and pumps. I would say 20 years ago, this system will work fine without coatings. But with the new emission regulations and the requirement for higher efficiency, so these components were made with much tighter tolerance. We're talking about a few microns. So metal-to-metal contact will instantly cause a seizure. So the DLC type of coating is kind of a standard solution for this application. And also engine valves, where you have thermal erosion, adhesions, and those issues can be mitigated by chrome nitride type of coatings, which offer better performance than something like hard chrome. And bearings and gears, we talk about these for high-speed applications, has been well adopted in the automotive industries and also for other vehicles. So I think I used it a lot of times to dive into the details. Here are some applications related to automotive, related to cars. I will skip, these are kind of deep dives. I will try to skip these few slides to save some time, but feel free to review them offline after you get these slides, the previous presentation slides. And I will jump into this slide, which talk about this is probably a slide created in 2018. But the main point over here is, like I said, the tribological issues or applications will have been studied or well established way before this time, right? Maybe a decade or a couple of decades. So for the future development, we ought to focus on something beyond tribology. So that's the future trend. And for example, some of the PVD coatings are very responsive or have a higher or faster response to temperature change compared with the traditional thermocouples. And some of the PVD coatings has a perfect linear response, electrical response to strains. We can use that as a strain gauge. So we can deposit these PVD coatings on moving components, for example, in automotive, in the cars, right? So to create onboard sensors. Or we can use the coating to modify the surface energies or the wettability of the surface. For example, for molding tools, I want to create this easy release function between the workpiece and the molds, and also provide a wear protection to those molds because the molds are very expensive. Or for plastic gears, reinforced with carbon fibers or glass fibers, those fibers are very abrasive to the counter surface. So we will lay down diamond-like carbon type of coating on top to enhance the friction and reduce wear to the counter surface. Or we talk about the electrical conductivity of the coating. It can modify the static charge situation on the surface. So on and so forth. We can brainstorm, endlessly for different applications. And I believe this is the last slide of my presentation. I don't know how many people survived so far, but I really appreciate your time and congratulations. You probably can get the education credit from SAE. I try to salute the big names in tribology and coatings during the presentation, and some of them are associated with SAE. I hope that leave a mark in your memory. And down the road, if you come across PVDs or surface engineering issues or questions, please feel free to get a hold of me. I would be glad to offer my help or direct you to a good resource. So with that, I would like to give the floor back to Troy or Tim for any questions the audience may have. Thank you.
Yeah, thank you, Bao. That was fantastic. Tim, before we get into the Q&A session, did you have any comments or?
No, I think it was a great presentation. A topic I did not know a lot about, but it was very detailed, and certainly appreciate your time. I did check on that Harris you showed, the researcher. I could not find him in the current listing for SAE, but I don't have full access to all the members. But like you said, I'd be surprised if he wasn't a member of SAE. So thanks again. Great presentation.
Thank you.
Yeah, with that, and I hope I pronounced the names correctly. So if I don't, please correct me. But Budadeb Mahakul, you had a question? If you want to unmute yourself and ask directly, that would be great.
Yes. So I think I wrote my question in a note form. The question was pertaining to using coatings for reciprocating components that have clearances of 1 micron. Would a PVD coating be suitable for that?
So if I understand correctly, So you want to identify a particular type of PVD coatings that only a few microns, but can extend the wear life of a component.
Yeah. So what I'm talking about is, let's say we have something which has 1 micron clearance, right? And is there a PVD coating that can be applied for such tight tolerance?
Mm-hmm. Yeah. So, like I mentioned, the coating is typically we're dealing with microns or submicrons thickness. So that's the one of the specialty of the material because we don't need much of this coating due to its high wear resistance properties. And also that's benefit will provide you to not necessarily change the existing design. So you can simply put this coating on the existing geometry without causing any tolerance issues.
How long do these coatings last? Typically.
So, yeah, like I mentioned, the wear and friction is a system behavior. So it really depends case by case, right?
Mm-hmm.
And what kind of contact conditions, lubrication conditions, and the materials and speed at the contact interface and contact pressure, everything.
Mm-hmm.
But there are quite a few situations where we observed the coating will extend the wear life of the components by order of magnitude. So that's a pretty typical life expectancies by the PVD, or especially for the diamond-like carbon type of coatings. But again, like I said, every situation is different.
Right. I have one final question. I'm not trying to steal anybody else's time, but I just can't
You're
resist
fine.
not asking this. You were talking about hydrogen E. I didn't quite follow.
Mm-hmm.
Where is hydrogen coming into this picture of your coatings?
Oh, sorry. No, that was not what I meant. The H over E, the H stands for hardness. Sorry, I wasn't clear about that probably. The H is stands for hardness, and E stands for Young's modulus. And I was trying to compare that with the Model factor, which is the Bernal hardness over Young's modulus, delivered in this research by Ted O'Burrow.
Okay, I got it. Now that's crystal clear. You're talking about hardness, not hydrogen. Okay.
Yeah, thanks for the opportunity for me to clarify that. Yeah, I guess you're probably not the only one get confused. Thank you for that.
Thank you. Excellent presentation. I enjoyed the evening.
Thanks for the comments.
Yeah, thank you, Buddha. Alexander Connery, sorry. I think you had a question. If you want to jump in.
Yes. I wanted to know if you had done any case studies on coatings inside valves in highly corrosive environments, such as the petrochemical industry.
I can only answer your question as with a general comment here, because I didn't in person perform that kind of study in person. But like I mentioned, the coating PVD coatings will provide a corrosion resistance to a certain level. Not for the engine applications. I saw some for some bearing applications or mechanical seals, where the coating did have the issues because of the substrate collapse due to corrosion. But the alternatives is we can apply a coating in different ways. For example, multi-layer coatings or much thicker coatings. Of course, you need to consider if you got the coatings get thicker, we will have a higher residual stress. But those are the typical ways we try to improve the coating, the corrosion resistance of the coatings. But in general, the PVD coating is not a real good corrosion protection tool. But compared to some other thicker coatings, for example, chrome plating or zinc platings, but it can still depend on the situation. It provides some certain level of corrosion resistance.
And a follow-up to that, independent of corrosion resistance, have the coatings been shown to improve the longevity of the sealing surface, especially on a metal-to-metal valve?
Mhm. Yeah, absolutely. As a matter of fact, seal surface is very often a good place for the DLC type of coatings because it provide a separation between metal to metal contact. In case of metal seals, of course, it's okay. So we talk about this, separately. So for metal to metal seals, it will create a separation between metal to metal contact and adhesive type of wear. It kind of provide an adhesive type of wear and reduce the friction and extend the life of the process of the seals. And for ceramic, for example, silicon carbide type of seals, the coating is still beneficial because it's low friction property. For example, DLCs. For the asperity contact situations at a start and stop situation, even the ceramic seals will have high temperature. A lot of times will affect the surrounding components, for example, like rubbers or plastics, will reduce the life of those components. But the DLC coatings will reduce the friction coefficient and reduce the contact temperature for start and stop, and therefore to extend the life of the surrounding components.
Awesome. Thank you.
So
Thank
did
you.
I hear that right, Bao? The coatings will help mechanical face or dual cone seals.
Mhm.
That's a good application.
Apparently it is through the experience of different manufacturers. But of course, I cannot talk too much detail about that. But
Sure.
theoretically, that is a good place for PVD type of coatings.
Hello, Bao. Thanks for the presentation. I am working on this value engineering cost reduction projects. So with these coatings, do you have any case study where we can reduce the cost of automotive component? I'm talking about truck part, Class 8 truck. So we can reduce the cost of component by applying the coating. Is there any avenue?
So as you can see, the coating process is a batch process, right? And the piece part cost of component of code for coatings is depending on how many parts you can pack into a single coating chamber. So for that reason, the coating cost is not, we don't consider the coating as a low cost options. Rather, it's considered as a improvement for the surface or the machine systems. So in the sense that you extended the component life and reduce the friction and improve the efficiency, so you get an overall lower cost of ownership for the customers. So it's not a low cost alternative for most of the applications. I couldn't think of there's any case it is, but it will provide those benefits still much more significant than just the coating cost to the customers. And in some situations that the PVD coatings is a good replacement for some existing or some like old technologies, for example, chrome plating or PDFE. Those are start to get phased out because of regulations. And the PL and the DLC type of coating will be a good replacement. That also true is also true for automotive applications.
Okay, thank you.
Sure.
Are there any other questions? Bao, I had a question regarding a comment you made, I think, on slide 40. The elastic strain properties. Were you suggesting there that the coatings could serve as a transmitter of, in other words, could serve as a load sensing technology?
Yeah, that's exactly what I was trying to lead to. And yeah, so for those onboard sensor applications, the PVD coatings, you know, we believe it would be a good option because it's more sensitive and it doesn't take space. You can simply coat it on existing components without adopting a bigger volume, you know, like the traditional sensors.
Interesting. Is there literature out there on this, or?
Well,
Or is
I can
this-
try to search, or I believe there's, you can probably search.
Sure.
No literature or even you know, published literature. There must be a lot of those results already posted out there. So, but I will do some search and see if what I can find.
Yeah. I mean, or if I don't know what you have that you've done internally there at Oerlikon, but anything you could share, I'd be interested in that.
Yeah, absolutely.
Dan Karlak, you posted a question. Would you like to unmute yourself and present that?
Yeah, just real briefly, I've been interested in this concept of antimicrobial, antibacterial protection. I think we see this advertised, for example, for appliances in our home. And I also saw that it was one or two of the items you had medical devices. And can you talk a little bit about that? Do you have any products that that do this? Give some sort of antimicrobial, antibacterial protection. I know this was a big issue in the early days of the pandemic. It seems to have quieted down a little bit, but can you talk about that? Is that something that you guys get involved with or not?
Absolutely. Thanks for the question. It's truly a very popular application for medical, in the medical field, and we do have a coating already in production. And if you go to our website, you can easily find a more detailed description about this coating and coating specs and how, or maybe even how it works for antimicrobial applications. Mainly, you have to dope the coating with some precious metal, and so the precious metal will serve as the antimicrobial functions, while the rest of the coating will serve as wear resistance or other functions. Yeah, this is a coating solution already we provided in production. So feel free to check out our website to find more detailed information.
Very good. Thank you very much.
You're welcome.
Bao, this is Tim Hicks. What's the revenue or the overall sales for Oerlikon Balzers? And then in comparison, what kind of competition do you guys have? Because it seems like you've got a pretty good broad application for your products. It looks like it's a pretty unique situation you guys are in.
Yes, I used to bring up that the revenue slide in presentations, but for this audience, I thought this is probably more technical rather than commercial propaganda. So I didn't have that slide, and I don't really have accurate numbers in my mind. I think it's somewhere around $1 billion or something, but I believe that number is posted on our website also. It's public, so it's out there. And you asked about the competitions. It's very interesting because for all these applications, for all these in different industries, they are at a different stage in terms of the S curves of the technology life cycle, right? Some of them at the early stage, where Oerlikon as the leading companies, Balzers as the leading company in the field of thin films, will put a lot of research and development work to develop those applications. But our competitions may or may not have that capability of developing the new technologies. So we're kind of in those fields. But so once you get the applications like engine applications, these applications have already become a commodity type of where the coating is applied. And we have a lot more competitions in this field, and these applications are already on the top of the S curve, and it started to go down. And so obviously, different companies have different strategies, right? And for us, we'll spend a lot more emphasis on newer technologies and push out new applications from the bottom up. I don't know if that answered your question.
Oh, I did. Thanks for that overview. Is it a privately held company?
No, it's a public company. Actually,
Public, okay.
private stocks.
Okay. And is there a factory at your location in Houston?
No, not in Houston. However, if you're in the Midwest, we have many coating centers around the Detroit areas. One coating center in Illinois, and overall we have about 19 coating centers in the United States alone.
Okay.
The closest coating centers to Houston is in Oklahoma City, and we also have one coating center in LAX on the West Coast.
That's good. You guys are looks like you're in all the key areas.
So interestingly, Tim, there is a facility that's a short drive from Chicago. So not saying we might hit Bao up for a tour sometime, but we might hit Bao up for a tour sometime.
Yeah, I would be more than happy to offer that if you guys are interested.
Yep, we have that on the recording, so it's noted.
Who else has questions?
I think the slide answered yours, Troy, right? It's aluminum as far as the substrate.
Yeah. I think slide 33 or 34 answered the question about cast aluminum as a substrate. Yeah, there might be an opportunity to have a discussion with you sometime, Bao.
Yeah, we do code aluminum all the time.
Okay, well, if there's other questions, we can wrap up. Troy, if you want to do the honors, I thank you again, Bao, for taking the time to present tonight.
Yeah, I really want to extend our warmest gratitudes to you, Bao. I think I really appreciated the technical level of the presentation, the tie-in of the pioneers to SAE. Thought it was extremely well done, and really appreciate the time and the thought that was put into this presentation. So look forward to collaborating some more with you.
Thank you, Troy, for the comment. It's my pleasure. Thank you for everybody's time.
Fantastic. Thank you, Bao.